So we have our last talk about quantum obfuscation, and then this time is the unitaries.
Okay. Thanks for the introduction, and also thanks James for providing a nice foundation for the audience. I'm Er-Cheng, and I'm going to present obfuscation of unitary quantum programs. And this is a joint work with Miryam. So first, what do we mean by a quantum program? At its simplest, a quantum program is just a quantum circuit which has a classical description. A more general quantum program can consist of a quantum circuit together with an auxiliary quantum state that assists in the computation, and such program has a quantum description. And to execute this type of program on an input, one can just apply the circuit Q jointly on the input and the auxiliary state side to produce the output. But one caveat about using such program is that the auxiliary quantum state might be ruined after a single evaluation. So quantum programs may not allow multiple evaluations in general. But in most applications, it's preferable to have a reusable program. So by default, we will be considering quantum programs that are reusable. And today, I will focus on quantum program with auxiliary state. And throughout the talk, I will use quantum circuit to refer to circuit and quantum program to refer to circuit with a state. So let us briefly recall what obfuscation is. So initially, we have the original program, and after obfuscation, we want to get an obfuscated program, which is preserves the functionality, but appears unintelligible. And ideally, we will want to obfuscate all kinds of quantum programs. However, obfuscating quantum programs is a tough nut to crack. As mentioned in James' talk, people have been exploring a variety of obfuscation notions and functionalities. So for example, Broadbent and Kazmi shows how to obfuscate quantum circuits that have a logarithmic number of T-gates. And they achieve quantum I/O in the plane model. Subsequently, people have made some other efforts, but still far away from obfuscating general quantum programs. And given that obfuscating quantum programs is hard, people are willing to consider stronger models than the plane model and see if we can obfuscate more programs in stronger models. And one model that turns out to be very useful is this classical oracle model. And this is a model where everyone can turn efficient classical circuits into classical oracles for free. One can view this model as assuming ideal obfuscation for all efficient classical circuits. And anyone who obtains these classical oracles can make superposition queries to these oracles. And under this model, people have been able to obfuscate more programs. And this model is also reasonable to work with because these classical oracles can later on be heuristically instantiated using post-quantum I/O. So in the classical oracle model, Bartušek, Kitagawa, Nishimaki, and Yamakawa obtained a quantum virtual black box obfuscation for efficient quantum circuits that compute deterministic classical functions. And more recently, Bartušek, Brokarsky, and Vaikutinathan achieved ideal obfuscation for efficient quantum programs that computes deterministic classical functions. And note that these results can achieve the strong notion of VBB or ideal obfuscation because they work in the classical oracle model instead of the plane model. And so their obfuscated program in these schemes will carry a classical oracle. And building on these breakthroughs, our work takes the next step. In the classical oracle model, we obtain an ideal obfuscation scheme for every efficient quantum programs that implement unitary transformations. So this is the first result that can obfuscate a broad class of quantum programs with quantum functionalities. In previous work like BBB24, they obfuscate programs that compute a classical function f, which has classical inputs and classical outputs, and are deterministic. But now we would like to consider a program that computes a quantum mapped phi that sends a quantum state to a quantum state. A general quantum map can always be expressed as first embedding the input state rho into a larger space, and then applying a unitary on this larger space, and finally applying a partial trace to produce the output. And such general quantum mapping covers a wide set of computations, such as the quantum Fourier transform, pseudo-random unitaries, state preparation, or quantum error correction. And in this work, we will focus on programs that implement unitary transformations, which has the effect of applying some unitary operator on the quantum input. So one notable difference between a unitary transformation versus a general quantum mapping is that now a unitary transformation does not have this embedding and partial trace. So a unitary transformation will have the same size of input as the output. But even with this restriction, unitary transformations are still very expressive. They cover all classical functions after they've been made reversible, and also the examples of, say, quantum Fourier transform and pseudo-random unitaries on the left. And the examples on the right correspond to more general quantum maps. Yeah.
I think the existing PRE constructions cannot be implemented just using unitaries. The circuit that implements PRUs, they actually involve adding ancillas and then tracing out.
Yeah, so here, like, we are allowed to use ancillas in the psi-aux, the auxiliary state. So here we care about like the input and output, whether it's the effect of from input to output is a unitary transformation.
So it's not the case that you're considering the circuit itself to be unitary. Instead, you're looking at the circuit being functionally equivalent.
Yeah, that's right.
You can also have PRUs with nodes, but conjectures. There are PRUs, at least conjectural one, without ancillas.
Yeah. Any questions? Okay. So can we obfuscate such programs? The answer is yes for unitary functionalities. So our results are threefold. So first, we properly define the notion of ideal obfuscation for quantums with unitary functionalities. So coming up with a proper definition here requires some care because we are dealing with quantum functionalities here. And then we give a construction in the classical Oracle model that achieves this notion of ideal obfuscation. And additionally, we prove that our obfuscated programs, which carry auxiliary quantum states, are reusable. So here's our journey today. We will first define ideal obfuscation for unitary functionalities, and then we will see the construction and some of relevant components. Okay, so what is a reasonable definition of ideal obfuscation for unitary functionalities? And as I mentioned before, coming up with a meaningful definition now is non-trivial. So existing works consider ideal obfuscation for classical functionalities. But now, since quantum behaviors are more complicated, the standard definition will not directly work. So let's take a closer look. So the core philosophy behind the notion of ideal obfuscation is the intuition that the only way to use an obfuscated program is just to run it on some input. But is this statement still true in the quantum setting? Given the quantum program, we can of course run it on the input, but we can also perform a quantum rewinding of the program. And moreover, we can perform a quantum controlled execution of the program, which execute the program if the control qubit is in state 1, and does nothing if the control qubit is in state 0. So, so classically, if the quantum program implements a classical function, these operations are all equivalent to computing f. But quantumly, if the quantum program implements a unitary transformation, these quantum operations can enable new power that go beyond just evaluating u. So let's explore what these new functionalities are. So suppose we're given a quantum program that computes a unitary transformation u. The rewinding of the program will give us u inverse. And performing some quantum controlled execution can give us this controlled u inverse au for every efficient operator a. So one might wonder why we cannot simply apply quantum control execution of the program to directly compute control u. So a short answer is that in a quantum control execution, the control qubit might become entangled with the auxiliary quantum state of the program. And so this would prevent you from computing control u in some cases. But we can show that this issue can always be avoided if the control execution contains both a forward execution and a rewinding execution of the program, which corresponds to controlled u inverse au here. So with access to the program, one can always compute u inverse, and control u inverse au for every efficient a. One can further show that all of them can actually be computed with just black box access to a single control u inverse a0u for a fixed unitary a0. For example, we can choose a0 to be the swap operator on 2n qubits. So, yeah.
Efficient, because I would imagine that you can also efficiently run u if you are given an obfuscation of u. So why couldn't you run control u inverse u versus u a I?
So if you're given the obfuscated program, you will not know like what you are implementing. So if you knew an efficient operator A, like you know what A you want to apply, then you can apply control u inverse au without knowing what the program is implemented, where the program is actually implementing u. Does that make sense? So given the program that implements u, you might not know that it is implementing u. So you cannot choose A to be u because you just have the program and don't know u. Yeah.
So all of this is just because he has the code, a code, not just
Yeah.
a box.
This is because you have the code.
Yeah, okay.
Yeah, exactly.
Sort of unavoidable in that sense.
Okay. So this observation leads us to the following definition of ideal obfuscation for unitary functionalities. So in our definition, we will require that the obfuscated program can be simulated by a simulator that does not have the program, but is given oracle access to control u inverse a0u rather than just u.
Which A of its choice.
So this a0, you can think of this as the swap operator, like the fixed a0 in the previous slide. So this definition exactly reflects the additional power that can be computed with white box access to the program, because you can use control u inverse a0u to compute all the things that mentioned in previous slide. And so we call a scheme that satisfies this definition an ideal obfuscation for unitary functionalities. And it is noteworthy that when u computes a classical function, having black box access to this controlled U inverse A0U is equivalent to having black box access to F. And so our definition recovers the standard definition of ideal obfuscation when the unitary computes when the program computes a classical function. Okay. So now we have defined, oh, yeah.
So sorry, maybe we're missing something. What is A0 in the bottom case?
So you can think of it, it's the swap operator, yeah.
And you're saying just having control access, you can implement U dagger?
Yeah.
What about complex conjugate of U and transpose of U?
So you will not be able to compute that if you're given a program. So like in general, like a program that computes U might use the oxychron state to perform some like T gates. But like it cannot use those states to compute T conjugate. So you cannot, in general, you cannot use a quantum program to compute the conjugate or transpose. Yeah. Yeah. Any other questions? Okay. So now we have defined ideal obfuscation for unitary functionalities. Let us turn to constructing such a scheme. Before presenting the details, I would like to highlight a few high-level points. So, yeah. Oh, I mean ideal obfuscation? So this is actually stronger than VBB. So here, the simulator will not depend on the adversary. Well, in VBB, the simulator can depend on the adversary.
So there are only possibilities, the Barat and whatever, the extended Barat and our control.
So because now we're working in the classical Oracle model, so we can avoid this impossibility. Yeah. So our construction is built upon BBB24's construction. So I will first introduce the common template underlying BBB and our construction, and then discuss the aspects that the BBB24 approach can be enhanced, and then explain how our refinements address these problems. So we'll start with the following template. The obfuscator will want to encrypt the program and some workspace and provide the ciphertext state along with the functional key or homomorphic key as the obfuscated program. And to evaluate on the quantum input, the evaluator will use the key and the input to perform homomorphic computation over the ciphertext state. And after performing multiple steps of homomorphic computation, the ciphertext state will now encrypt the computed output. And at the very end, the evaluator will use the functional key again to read out the quantum output in plain text. So to realize this template, we'll need two things. First, we need a convenient model of quantum computation. And second, we want to apply the quantum computation homomorphically over the ciphertext. And we want a way to decrypt only the final output. And note that here we will need both encryption and authentication because we want to ensure the privacy of the program. And we also want to prevent the adversary from reading out plaintext information from maliciously computed ciphertext. So let's start with the first item. So let's consider the following model of quantum computation, which is actually the linear plus measurement program in earlier James' talk. So we first focus on the case of classical inputs and outputs. So the computation can be specified by an initial quantum state of m qubits on the wires, and a sequence of measurements each specified by a gate Gi, consisting of C0 and Hadamard gates. And the classical function Fi, parameterized by x R1 through Ri-1, and map m-bit strings to 1 bit. And to execute the program, one just plugs in the input x as the parameter to the first function f1. And now compute f1 in the G1 basis coherently and measures the computation output to get a 1-bit measurement outcome R1. And then we use x and R1 as the parameter for f2, compute f2 in the G2 basis coherently, and measure the function output to get a 1-bit measurement outcome, R2, and so on. So in other words, this execution is adaptively choosing the next function to compute based on prior measurement results. And finally, the measurement outcome of the last function will produce the output y. So at a high level, this model of computation is performing something quantum because these measurements are across different bases. And it achieves universal quantum computation because these adaptively chosen functions make the computational model sufficiently expressive. And BBB24 shows that every efficient quantum program can be efficiently compiled into this form with efficient functions Fi. So the compiler would output a state that consists of the program, some memory, and resource, along with the descriptions of Gi and Fi. Okay, so we've mentioned the second thing that we need is to execute this quantum computation homomorphically over encrypted and authenticated states. And this leads us to the notion of quantum authentication scheme. So here, an authentication scheme allows a person with a secret key to encrypt a state into a ciphertext state. And the decryption algorithm can detect if an authenticated state has been modified. And if not, the decryption algorithm can recover the original state. So BBB24 proposes a quantum authentication scheme that supports homomorphic measurements in the CNA plus Hadamard basis. In such a scheme, one can apply homomorphic computation of G over the ciphertext state, where G is C0 plus Hadamard gates. So after this homomorphic computation, one obtains the ciphertext of the computed result. And moreover, the measurement result of this ciphertext state in the standard basis can be classically decoded using the secret key to obtain the actual measurement outcome V, as if the initial state has been measured in the G basis. And their scheme also comes with the classical verification algorithm that detects invalid measurement results. So here we will always assume that the classical decoding algorithm first performs the verification and only decodes if the verification accepts. So for such a scheme, there's a way to homomorphically perform the computation that we've shown before. And this can be done if the evaluator holds a classical oracle, which computes a classical function composed with decoding in the G basis. So let's see how to use this classical oracle to homomorphically measure the output of F in the G basis over the ciphertext state. So one can first apply homomorphic G and then make superposition queries to the oracle using the ciphertext state as the input. And this will result in a new ciphertext state that authenticates the computation result of F, of the residual state of F, along with the decoded computation outcome R. And finally, one can apply the inverse of homomorphic G. And so after this whole process, one obtains an authenticated state and a plaintext outcome. And the information held by the states is the same as if one had computed F in the G basis directly on the initial state, and then the measurement outcome is given in plaintext, while the residual state is given under authentication. So such a scheme would be very powerful. But what about its security? So BBB24 established several security properties such as privacy, integrity, and public verifiability. But their scheme does not fully cover the case where the adversary have access to classical oracles with partial decoding abilities. And to remedy this, we propose a definition of simulation security of their scheme, in which the adversary can have partial decoding power. And we show that their scheme achieves the notion of simulation security. And this notion of simulation security turns out to be crucial when we analyze our obfuscation scheme for unitary functionalities. So our characterization of security actually allows us to reinterpret the scheme as a functional quantum authentication scheme. So in more detail, we can view each oracle as a functional key. So a functional quantum authentication scheme will now consist of a setup that generates a master secret key, an encryption algorithm that encrypts a state, a key generation algorithm that, given F and G, generates a functional key for computing F in the G basis, and an evaluation algorithm that allows the functional key holder to compute over the ciphertext state to learn the function output of F in the G basis in plaintext. So we would like to capture security when the adversary has the authenticated state and some functional keys. So at first glance, the adversary might try to do a lot of things, such as querying the oracles in superposition on some state that's derived from the authenticated state. So to capture security, we propose the simulation security, which says that the adversary can only use these functional keys and the authenticated state to do the computation allowed by the functional keys. So in more detail, our simulation security requires that the real world is indistinguishable to the ideal world, where in the ideal world, the adversary is only given the encryption of a dummy state and the basis G, and also oracle access to a simulator. And the actual state is held by an ideal functionality who computes F in the G basis honestly upon being queried by the simulator and replies the simulator with the function output only. So under this definition, our simulation security says that the adversary can only learn information that is being granted by the functional keys and nothing more. So using our functional quantum authentication scheme, we can now show how to construct an obfuscation scheme. Let us first obfuscate programs with classical inputs and outputs. So the obfuscator can just encrypt the program, memory, and resource and provide the ciphertext state along with classical oracles, capital FIs. And what each capital FI does is to first decode in the GI basis compute those little fi and outputs a pseudorandom label of the computation result, Ri. And the last oracle is defined to output the result Y in plain text. So to execute this program, the evaluator just has to use its input X to perform homomorphic computation over the ciphertext. And along the way, the evaluator will only learn the pseudorandom labels in the intermediate steps, and will learn the final output Y in plain text. And to make this scheme secure, we also need to ensure that the same input X is consistently used across these different oracle calls. And this can be achieved using a one-time tokenized signature scheme, which I will not explain in this talk. But to use this scheme, the obfuscated program will additionally contain a one-time quantum token. And the evaluator has to use this token to sign the classical input X. And the oracles will always check if the input is properly signed. And this one-time token only allows signing on one input at a time. So far, this is essentially the construction of BBB24. And we want to see how to handle quantum inputs and outputs. So why can we directly achieve quantum inputs and outputs? The main obstacle of the previous method is that first, the model of quantum computation only considers classical inputs and outputs. And moreover, we have been using the classical oracles to interpret the classical input, check for input consistency, and deliver the classical outputs. So there are two questions. First, how can the model of quantum computation support quantum inputs and outputs? And also, how can these classical oracles handle the same task for quantum inputs and outputs? So our solution to this is to incorporate quantum teleportation into the framework. So to explain, we will let the obfuscator additionally prepare EPR pairs for the input and EPR pairs for the output, authenticates half of the EPR pairs along with the program and resource, and the obfuscated program will now also contain all these states. So later on during the evaluation, the evaluator can take its quantum input and perform quantum teleportation of its input using the half EPR pairs for the input. And this will result in the classical teleportation result X. So the evaluator then uses X to perform homomorphic computation along with homomorphic teleportation of the quantum output. And this would yield a classical teleportation result Y, which is still encrypted. So the evaluator then uses the oracle to read out Y in plain text and use Y and the other half of EPR to recover the quantum output. Okay. So from a security standpoint, you might wonder, what if a malicious evaluator tries to declare an incorrect teleportation result? And in this case, the execution will still correspond to the evaluator having chosen some other quantum input for the computation. So the malicious evaluator will receive a quantum output for the input they effectively selected. And what about a malicious evaluator that tries to declare a teleportation result that is inconsistent across oracle calls? Well, thanks to the use of tokenized signatures, we have ensured that such an attempt will be rejected because the evaluator will not be able to produce valid signatures. So let's put everything together. the obfuscator will produce states on the left and several classical oracles together as the obfuscated program. And to execute the program, the evaluator will first teleport the input using EPR to produce a classical outcome, perform homomorphic computation on the ciphertext, and then use the final oracle output Y to recover the quantum output. Okay, so here one might be worried that these EPR pairs will be destroyed after a single evaluation, right? So a good news is that we show that this issue can be resolved if we focus on obfuscating programs with unitary functionalities. So in particular, we have a generic way to restore the state to its original state after evaluating the obfuscated program. So the idea is that, so our obfuscated program have two components, an oracle circuit Q and a state psi. So the state psi ox here corresponds to the EPR pairs and the authenticated states. And the oracle circuit corresponds to the evaluation process. And since our obfuscated program still computes a unitary functionality, after the evaluation, the output U of rho will be in a tensor product with the residual state, psi prime. And moreover, we can show that this state psi prime will be independent of the input rho. And so if we were to rewind the circuit Q, we will recover the original auxiliary state psi ox. And this does not depend on that we started with U rho. So in fact, Q inverse psi prime can be viewed as a program that implements U inverse. And after this computation, you always recover psi ox. So this picture will not be directly useful because at the end, you didn't get U of rho. So what we can instead do is to consider this new program, which first applies Q on the input and auxiliary state, and swaps out the quantum output with the dummy new input, say 0, and then apply Q inverse. And this new program will compute a U inverse, and restore the auxiliary state at the end. So one can use the program to compute U and U inverse multiple times. And this argument, and this argument also applies if the program implements a unitary, but with a negligible approximation error. So let's wrap it up. We see how to well-characterize ideal obfuscation for unitary functionalities. And we see how to construct obfuscation for all quantum programs with unitary functionalities. And our obfuscated programs are reusable for multiple evaluations. And along the way, we also attain a functional quantum authentication scheme with simulation security. So let me end with some open problems and future directions. So first, can we construct even more general functionalities, such as isometry or isometry plus partial trace, which includes randomized classical functions? And second, can we obfuscate quantum circuits into quantum circuits without auxiliary quantum states? And can we weaken the assumption to indistinguishability obfuscation? Another interesting direction is to explore connections with quantum complexity theory. So our obfuscation scheme can be seen as a method for instantiating unitary oracles using classical oracles supplemented with quantum states. So this raises the possibility of translating complexity results that are relative to quantum oracles into one that rely only on classical oracles, but with the caveat that we need to have an additional quantum state in the setup. So we're still exploring like whether there's a setting that might benefit from this approach. And this concludes my talk. Thank you. Oh, yeah, sorry.
How is the last part related to, is this last part related to unitary synthesis?
So I think here we only obfuscate efficient unitaries. So I think in unitary synthesis, we want to look at inefficient unitaries. Am I correct on this?
Isn't your result unconditional?
Yeah, so if we assume classic oracles and random oracles, it's unconditional, but like, let's see. So we need to start, so we need to start with an efficient implementation, like efficient program that computes a unitary. So I'm not sure like if now, because like I think in unitary synthesis, we will look at inefficient unitaries. And I'm not sure whether this would make a difference. Yeah.
So I guess this is for like a few slides ago when you introduced your security definition, you claimed that like the security you achieve is that the program itself can be simulated, and you're saying this is stronger than VBB.
Yeah.
I guess I can see this is true in the plain model, but here you are considering classical oracle model. So can you clarify like why that's still true? Because you also need to simulate the classical oracle.
Yeah. So so here like in ideal obfuscation, the simulator would have to produce the quantum state, the quantum circuit and the quantum state, and simulate the classical oracles. And in these simulations, it cannot depend on what the adversary is doing, which differs from the case for VBB, where in VBB, the simulator can possibly depend on what the adversary is doing.
So should I think of the security definition as like you create some implementation of the oracle that the adversary could compute or rewind, and the security will still hold?
So it's a bit different. So in the security, like we don't directly give an oracle to the adversary, and instead like our simulator like receives queries from the adversary and simulates the responses.
It's like a stateful simulator, right?
Yeah, it's a stateful.
It would be non-stateful.
Yeah.
The real oracle is not stateful, but the simulation.
Yeah. Oh yeah.
You comment on what goes wrong when you consider isometry instead of unitary?
So in isometries, the output will be the size of the output will be larger than the size of the input, and so like we can think of an isometry as the process of like appending an auxiliary zero and apply a bigger unitary on the whole system. And so to obfuscate isometries, you need to ensure that like the evaluator would not be able to put other things on the ancilla states, like not put ancilla zero, but put some other things and apply it to get some other outputs.
So it's an issue with the security potentially, not with correctness.
Yeah, it's with security.
Okay, so more questions?